Welcome to a lecture series on matrix analysis with applications. In the last lecture, we have seen that how we can find out inverse of a linear transformations. We have seen that if T is invertible, that is T is 1 1 and on 2, then T inverse is also linear and invertible. In this lecture, we will discuss that how we can find out a matrix associated with a linear transformation. Okay. Let us suppose that V and W be vector spaces of dimensions n and m respectively. Okay. Let us suppose these two are finite dimensional vector spaces of dimension n and m over the field F. Let B1, which is given by V1, V2 up to Vn, be an ordered basis of V, and B2, which is W1, W2 up to Wm, be an ordered basis of W. Let T from V to W be a linear map, be a linear transformation. Okay. Now, what we are discussing basically here, you see, we have a linear transformation T from V to W. B1, which is given by V1, V2 up to Vn, is an ordered basis of V, and B2, which is given by W1, W2 and so on up to Wm, is an ordered basis of W. Okay. Dimension of V is n, dimension of W is m. Now, if you take T of say Vi or V1, suppose first you take T of V1, T of first element. Now, T of first element will be some element in W, and that element in W can be expressed as the linear combination of element of the basis of W. So that means this T of V1 can be written as alpha 1 1 W1 plus alpha 1 2 W2 plus and so on alpha 1 m Wm. Okay. Or you can write it like this, alpha 2 1 alpha m 1. Okay. These are the scalars, you see. Similarly, if you want to write out say T of Vj, where j is running from 1 to n, so it will be alpha 1j W1 plus alpha 2j W2 and so on up to alpha mj into Wm, or it will be written as summation I running from 1 to m alpha ij Wi, and j is running from 1 to n. So, that means each of the element of this B1 can be expressed as linear combination of elements of Wi's or Wi's. Now, if you take the first element V1 and T of V1 is given by this, and these scalars are called coordinates of this V1, I mean T V1, sorry. The coordinates of T V1 are alpha 1 1, alpha 2 1 up to alpha m 1. The coordinates of V2 will be similarly alpha 1 2, alpha 2 2, alpha and so on up to alpha m 2. So, if we represent a matrix corresponding to this like this, the first coordinate of T V1 as a column vector alpha 1 1, alpha 2 1 and so on up to alpha m 1. The second vector is alpha 1 2, alpha 2 2 and so on up to alpha m 2, and the last one is alpha m 1 n, alpha 2 n and so on up to alpha m n. So, this m cross n matrix, this matrix corresponding to this linear transformation with respect to the basis B1 and B2 is a matrix associated with T with respect to the ordered basis B1 and B2. Okay. So, this is the same A which we have discussed, and this is called the matrix of T relative to the pair of ordered basis B1 and B2. Okay. Now, to understand this, let us discuss few examples or few problems based on this. The first problem is Let us consider T from R2 to R3. Okay, the simple example, and T is given by T of x1 x2 is given by x1 plus x2, 2x1 minus x2 and 7x2, and the basis of the first basis of R2 is, the ordered basis is 1 0 and 0 1, the standard basis, and the basis of R3 is 1 0 0, 0 1 0 or 0 1 0 0 1, the standard basis of R3. Now, we have to find out the matrix of T respect to with respect to the basis B1, ordered basis B1 and B2. So, how we can find out that matrix? So, let us see here. First we find T of 1 0, this T of 1 0. T of 1 0 from here is, it is 1, it is 2, it is 0. Now, what will be, and this is nothing but 1 times 1 0 0, 2 times 0 1 0, and of course 0 times 0 0 1. So, what are the coordinates of this vector T 1 0? The coordinate of this vector are 1, 2 and 0, and you write this as a column of the matrix of T. Again, T of 0 1 is nothing but, you simply take 1, it is minus 1 and it is 7, which can be written as 1 time 1 0 0 minus 1 times 0 1 0 and plus 7 times 0 0 1. So, the coordinate of this vector is 1 minus 1 and 7. So, the matrix associated with this linear transformation corresponding to the bases B1 and B2 is given by the first coordinate 1 2 0 as a column vector 1 2 0. The second one is 1 minus 1 7 as a column vector 1 minus 1 7. So, this will be the matrix associated with this linear transformation T corresponding to these standard bases of R2 and R3. Say now we have a second example. You see, the second example is, determine the matrix of T with respect to the bases B1 and B2, where T is given by this expression, B1 is this and B2 is this. So, how we can find this? So, now T is from R3 to R2, okay, and T of x y z is given by x plus y and y plus z. So, B1 is the basis of R3 is given as 1 1 1 is given to us 1 0 0 and 1 1 0, and basis of R2 is as 2 3 and 1 0. So, of course, corresponding to different bases for the same linear transformation, the matrix will be different. If you have this linear transformation, but we have a different basis of R3 and R2. So, there will be a different matrices of this linear transformation corresponding to the basis B1 and B2. Okay. Now, suppose, so of course, the order of the matrix will be 2 cross 3, it is clear from here. Okay. So, what is T of 1 1 1? First we find this T of 1 1 from here is 2 comma 2, okay. And now this can be written as, you have to write this as a linear combination of 2 3 and 1 0, okay. So, it is 3 and we want 2, so it is 2 by 3 times this, then only it will become 2, because no second component here. Now, it is 4 by 3 and you want to make it 2, so it will be 2 by 3, then only it is 6 by 3 means 2. So, the coordinates of this vector with respect to this basis is 2 by 3 and 2 by 3. Now, if you take T of 1 0 0, T of 1 0 0 here is, you take 1 plus 0 is 1 and 0 plus 0 is 0, which is 0 times 2 3 plus 1 time 1 1 0. So, the coordinate of this vector will be 0 1. Now, T of 1 1 0 will be, you see 1 plus 1 is 2 and 1 plus 0 is 1, and this can be written as, you see, you want to write it as a linear combination of these two vectors. So, you want 1 here, so it is 1 by 3, and you want 2 here, 2 by 3 means 4 by 3. Okay. So, the matrix corresponding to this linear transformation with respect to these two bases will be the first coordinate 2 3 2 2 by 3 2 by 3 as a column vector, the second vector, the second coordinate 0 1, the third vector is 1 by 3 and 4 by 3. So, it is of order 2 cross 3. So, this will be the corresponding linear transformation. Okay. The third problem is, you consider a linear map, I mean linear transformation D from P3 to P2, which is a differential map. Okay. Now, we have to calculate the matrix of D relative to the standard bases of P3 and P2. So, how we can do that? Now, here D is from P3 to P2, and D of F is simply F dash, or D of P is simply P dash. Okay. With respect to the standard basis. So, standard basis of P3 is 1 x, x square and x cube. A standard basis of P2 is 1 x and x square. Now, what will be D of 1? D of this element 1, because it is a differential operator, it is 0, and 0 can be written as 0 times 1 plus 0 times x plus 0 times x square, the linear combination of these 3 elements. Differential of x is 1, which can be written as 1 times 1 plus 0 times x plus 0 times x square plus 0 times x cube, 0 times x square, because this element is in P2. Now, what is d of x square? D of x square is 2x, which is 0 times 1 plus 0 plus 2 times x plus 0 times x square. And what is d of x cube? It is 3x square, which is equal to 0 times 1 plus 0 times x plus 3 times x square. So, what is the corresponding matrix? Corresponding matrix will be, you see, here the coordinates are 0 0 0. So, as a column 0 0 0, here coordinates are 1 0 0 1 0 0, here coordinates are 0 2 0, which is 0 2 0, here coordinates are 0 0 3 0 0 3. So, this will be the matrix corresponding to, it is of 3 row 4 columns. Yeah. So, this is a corresponding matrix with respect to this linear transformation corresponding to these two standard bases of P3 and P2. Now, if a linear map is known and a standard and the bases are known, then we can find out a corresponding matrix. Okay. Now, if a matrix is known and bases are known, then can we find out a correspondingly linear map from V to W? So, the answer is yes. So, how we can find this? Let us see here. So, let us suppose B, a matrix B which is given by Bij of order m cross n be given. Now, using this matrix B, we shall define a linear transformation T from V to W, where V and W are the vector spaces of dimensions n and m respectively. Now, to understand this, let us suppose B1 which is given by V1 V2 up to Vn, and B2 which is W1 W2 up to Wm be the ordered bases of V and W respectively. Then how we can find out the correspondingly linear transformation from V to W? So, you see, we are having T from V to W, a matrix B which is Bij of order m cross n is known to you. That matrix which is associated with a linear map corresponding to the bases B1 and B2. B1 and B2 are the bases of V and W. Okay. Now, again, so this matrix will be something like, you see, it is B11, it is B12 and so on up to B1n, it is B21, B22 and so on up to B2n. Okay. And it is Bm1 and so on up to Bmn. It is of order m cross n. Now, if you want to write the first element T of V1, okay, which is the first element of the basis of B1. So, this is some element of W. So, again this can be written as linear combination of elements of basis of W, which is elements of B2, and the coordinates, we know that the coordinates of this vector is always in the column vector, is always from the column. So, this T of V1 can be found as B11 of W1 plus B21 of W2 and so on up to Bm1 of Wm. So, this is known, the coefficients all Bij's are known and Wi's are known. So, similarly, if you want T of Vj's or Vj's, yeah. So, this will be, you see, B of Ij, okay, and it is Wi, and summation I is varying from 1 to m. It is T of Vj's and I is, yeah, j is running from 1 to n. So, if we know the T of all Vj's, then we can easily find out the correspondingly linear map. How we can find this? Let us discuss this by an example. You consider a matrix A of 1 minus 1 2 3 1 0. We have to find out a linear transformation T from R2 to R3 to R2 in each of the following bases B1 and B2. The first of all, the first one is standard basis of R3 and R2. So, how we can see this? T is from R3 to R2. Matrix A for both the problems is same. Okay. Now, standard basis of R3 is 1 0 0, 0 1 0 and then 0 0 1. The standard basis of R2 is 1 0 and 0 1, okay, that we already know. Now, what is T of 1 0 0? T of this element. Now, T of this element will be given by the matrix associated with this linear map correspond to these standard bases is this matrix which is given to us, and the first column correspond to the coordinates of the first vector, that is T of V1. So, this is nothing but 1 times 1 0, the first element of the basis, ordered basis, plus 3 times 0 1. So, that is simply 1 comma 3. Again T of 0 1 0 will be written as the second column, that is minus 1 times 1 0 and 1 times 0 1, that will be minus 1 comma 1. Now, T of 0 0 1 will be equal to 2 times 1 0 plus 0 times 0 1, which is 2 comma 0. Now, if you write any x y z in R3, so it can be written as x times 1 0 0 plus y times 0 1 0 plus z times 0 0 1. So, T of x y z will be equal to x of T of 1 0 0, because T is a linear map, y of T of this element and z of T of this element, and this is x into T of 1 0 0 is, this is 1 3 given to us, y of this is minus 1 1 and z of this is 2 comma 0. So, this will be x minus y plus 2 z comma 3 x plus y. So, this is the required linear map. So, if matrix is known and a correspondingly bases are known, then also we can find out the linear map. Okay. In the second example, if you see a second example where bases are this and this, so how we can find out the corresponding linear map? Again you can see here, again T is from R3 to R2 and A is given to us, which is 1 minus, which is same. Okay. B1 is 1 1 1, 1 1 0 and 1 0 0. B2 is 1 1 and 1 minus 1. Now, first you write T of 1 1 1, the first element, the coordinates are 1 3. So, 1 times 1 1 plus 3 times 1 minus 1, which is 4 comma minus 2. Now, T of 1 1 0 will be equal to, the coordinates are minus 1 times 1 1 plus 1 times 1 minus 1, which is 0 and minus 2. T of 1 0 0 will be equal to 2 times 1 1 plus 0 times 1 minus 1, which is 2 comma 2. Now, you express any x y z in R 3 as a linear combination of these 3 elements. Okay. You try to find out alpha, beta and gamma in terms of x, y and z. How we can do that? You can simply have 3 equations. You see alpha plus beta plus gamma from here is equal to x, alpha plus beta is equal to y and gamma is equal to z. So, from here we will obtain as beta equal to y minus z, and from here we obtain as alpha equal to x minus beta minus gamma. Okay. You see alpha plus beta plus gamma equal to x, alpha plus beta equal to y and gamma is equal to, okay, and alpha equal to z, sorry, because it is the alpha. Alpha equal to z means alpha is z, so beta will be equals to y minus z, it is okay. And how we will find gamma? So, gamma will be equal to, from this equation gamma will be equal to x minus alpha minus beta. It is x minus alpha is z and beta is y minus z. So, this is x minus y, z cancels out. So, this is x minus y. So, what is x y z? It is z times 1 1 1, okay, plus y minus z times 1 1 0 plus x minus y times 1 0 0, and T of x y z will be equal to z of T of 1 1 1, which is 4 minus 2, plus y minus z times T of 1 1 0, which is 0 comma minus 2, plus x minus y T of this, which is 2 comma 2. Now, you can simplify this and you can find out the correspondingly linear map from R 3 to R 2 with respect to these 2 bases B 1 and B 2. So, if we know the linear transformation T and the corresponding bases of V and W, then we can find out a matrix associated with T corresponding to those bases B 1 and B 2. And conversely, if you know the matrix and the bases of V and W, then we can find out the linear map. Okay. So, in the next lecture we will see some more properties of vector space and linear transformations. Thank you.